Okay, so let's just rewind to Friday as you fight your lunch. Okay, so these are the things we talked about on Friday. We talked about our first type of elastocapillary effect. In day one, we mainly spent talking about capillarity. And the first thing we talked about yesterday was this sort of elastocapillary effect that comes from the softness of the material, right? In particular, we talked about this thing called a wetting ridge. So this is, we did on day one, we did the Young-Laplace Dupré kind of contact geometry. Then we did the far extreme, the Neumann contact. This was Young-Laplace Dupré, except not on an infinitely stiff back substrate, but on a soft substrate, right? And remember, we had the equivalent of horizontal force balance in Young-Laplace Dupré. Here we have, and we didn't have anything like vertical force balance, because the understanding was substrate can do anything you need in order to compensate for any horizontal, any vertical forces you apply. Here we put in something for a finite substrate stiffness, and you see that the object starts, the substrate starts responding and deforming at some length scale. That length scale is called the elastocapillary length. It's made up of, the scale of the force is set by, the scale of the surface stress is set by one of the surface tensions acting over here. In fact, it's the blue one, the liquid vapor surface tension up here in the numerator. And this thing has to react somehow. We had this discussion about whether it reacts with the shear or the bulk. And as we said, for most of these soft solids that this audience should care about, the shear is considerably suppressed with respect to the bulk. So if it can respond by shear, it will respond by shear. And that's the object in the denominator. I remind you, for even something like a piece of plastic, say Young's modulus of 1 gigapascal, this is like 100 times, several hundred times softer than metals or your microscope slide. This LEC is of the order of, this is less than 1 nanometer. Nonetheless, we saw that if you make things a little bit softer, once you start getting into the fraction of a micron range, this wetting ridge may be really microscopic, but it can have a profound influence on droplet motion on that surface. If you try rolling a droplet on it, there's a huge drag from the substrate impeding the motion of the droplet, which normally, droplet motion speeds are set. The viscous term is always just the liquid itself, okay? It helps, again, it suppresses splashing, it suppresses spreading. So there's a number of ways in which this can show up. And then you can start engineering the surface to make the drop go here or the drop go there, depending on the substrate stiffness. That's the first thing we talked about. Then we said, okay, there is an entirely different kind of material deformability that we want to start talking about. And that's material deformability, not because the object is particularly soft, like this piece of paper, cellulose fibers plus binder, is not soft. Bulk piece of this object is most unyielding, and so is this. The reason this is deformable is because it's thin. So then we invested, I don't know, 20 minutes talking about how you start thinking about the elasticity of thin objects, how you abstract from E bulk and E shear, or from Young's modulus and Poisson ratio to slender bodies. And the idea was, we really, really don't want to care about what happens in the thickness of the object, unlike here, where we do care about what happens in the thickness of the object. We would like to abstract some plane, some imaginary plane in this object, and endow that plane with, rigidity against bending and rigidity against stretching. We sat down and thought a little bit, did some hand waving and some dimensional analysis, and we decided how these numbers must scale. This is for sheets. The bending modulus should go with the cube of the thickness and the Young's modulus. the stretching modulus should go linearly, and then it should have a Young's modulus in it. So the scale for a bulk material reduced to a thin object is the scale is set by the same material parameter. But additionally, there's a very, very strong thickness dependence. Okay, we did little tiny bit of hand waving to say for rods, this should be t to the 4th, t squared. Okay. One small thing I should have added over there is for a truly two-dimensional material, like if you're thinking about a piece of graphene, for example, there is obviously there's no thickness to be spoken of. And in those cases, often the bending rigidity and the stretching rigidity comes from actually two different physical microscopic sources. So for example, if you're thinking of a graphene sheet, bending it really comes from interaction from the pi-pi bonds, and pulling it comes from, actually stretching carbon bonds, okay, stretching covalent bonds. So these are not from the same origin, unlike here, where you started with a bulk material and then made it thinner and thinner. Okay. All right, just to get some feeling for how thin materials behaved, we spent another 10-ish minutes thinking about just the simplest possible buckling experiment, right? This one. You take a sheet or a rod. Now I only draw its midplane, and I push it this way. Okay. And we ask, at what value of displacement does the energy stored in compressing this? It can react by completely compressing, or it can react by going out of plane and not changing its length or anything in between. The places where these two extreme possibilities become sort of comparable in scale is a critical value scale by the size of this object, which goes as the stretching divided by the bending. This is thickness squared divided by dimension squared. Okay, so for something like this, that's a very, very tiny number. What it says is almost immediately when you apply displacement to this, it'll choose to go into bending. And the disproportion between these two grows very strongly with how far you are above this critical load. So again, this sort of standard theme in condensed matter that we talked about in the connection of bulk and shear happens over here. You have a cheap thing and an expensive thing. Don't think you will spend on the expensive thing. You will spend only on the cheap thing. The expensive thing will basically show up as a constraint that you'll try to avoid. This is sort of a standard thing that you see in many places in condensed matter. Okay, so in fact, well above this threshold, you basically, the way you will deal with this is not by writing bending and stretching separately. What you'll do is you'll say, I'm going to have a term that involves bending and a constraint that says I must keep my length, the length that you originally gave me. Okay, and the Lagrange multiplier that goes with that will end up being the tension on this object. Okay. Maybe it's useful to, we didn't do this in painful detail, but we sort of sketched out how you go from this. You can go to, at least in small slope, you can go to this kind of, from this energy, you can go to this Euler-Lagrange equation. Okay. All right, then we've, yeah. Question is, when do you start seeing effects of speed of deformation of objects? Everything we've talked about is quasi-static, okay, and will be till the end of this hour. The thing you have to work slower than is the speed of sound. So typically things here move very quickly, and it is not difficult in the normal things we do like this to be in this quasi-static regime. Of course, if you have the speed of sound also changes with the softness of the material. In this kind of situation, where you're doing elastocapillary effects with soft stuff, you will start seeing elastodynamic effects quicker than here, where the material is pretty rigid. Speed of sound is quite fast, kilometer per second. So don't do anything faster than a kilometer per second. Tearing and cracking are different, and the third dimension is important. Crumpling is fine. This kind of formalism is what's used to describe, for example, an object making sharp points like that. Okay, that's all fine. All right, so then what, any other? Okay. Then we spent some time thinking about elastocapillary effects. Back to elastocapillary effects, and we did this little tennis racket thing, which you may see with your hair, or you may see with wet paper, or whatever you've seen it with. You see this sort of tennis racket. I think once you see this, you'll see it absolutely everywhere. You can't unsee this anymore. Huh? And here, this kind of sealing up, this zipping up, is driven by a competition between two things. You're trying to protect this air-water interface, the surface energy of that, and you do that by sticking two pieces together. This thing would zip up all the way, except that it takes finite energy to bend this in a circle. And at some point that you start paying for. So the competition between bending and capillarity is captured in this length scale. This is what is elegantly called the Bandyopadhyay length scale. And that sort of gets this problem correct. That's this. That more or less captures this problem. If you want to capture this problem perfectly correctly, then you will treat this as an elastica exactly like this. You will solve this equation with the right boundary conditions at the neck, and you'll get the shape perfectly. I think we said yesterday, I think I had it on one of my slides, you get a 90% correct answer this way. 90% is all I strive for. Okay. Then we did something that was more interesting, this beautiful experiment from the ESPCI group, where they do this capillary origami. So this is explicitly two-dimensional looking object. This one, they try to fold something up in 3 dimensions. And you remember this? So it's a 3-dimensional experiment, but if you look at it a little bit closer, the design of the experiment is very artfully chosen to actually make it many interesting 2-dimensional cuts. They're taking this object, which is like a flower with petals, and each petal does something like this. Each petal does a Bandyopadhyay thing, pure 1-dimensional Bandyopadhyay thing. So it looks sort of 3-dimensional, but in fact, it's a nicely designed 2D experiment. Okay. I have a few more things to say about this, but before we go there, let me just tell you what the plan is for the next hour and 15. Okay. So what I want to tell you today a little bit about is, again, slender body stuff, thin sheets, thin rods, thin sheets really. It'll feel a little less linear progression than the last 2 days. At least it was a linear progression in my mind. But this will feel a little bit, but let me tell you what the driving theme is, and then maybe that will help you when I go and do this, you won't think, why are you doing that? So the idea is, I'm trying to look for slender body elastocapillary stuff that actually involves stretching. I told you, right? You suppress stretching wherever you can. You always try to bend. But I'm looking for situations in which stretching is likely or inevitable, those kinds of things. And basically, the 2 things I'm going to try. One is to try and really get something wrapping around in 3 dimensions. And maybe that'll involve stretching. And the other is put something under tension and then start poking it. And that maybe will also excite this, this mode. Okay, that's what, so I'll cut in and out a little bit. I'll tell you about why tension, where you get the tension from. I'll tell you a little bit about why putting things, wrapping things is useful. But also I will start early on by showing you that I'm going to really now work with bending modulus quite a bit. And see that there's really a few regimes in which you can work. Okay. All right. Let me now rewind to capillary origami and say one or two more things. So what was going on in all of this was it was a nicely chosen parameter regime by these folks. So here's the parameter regime for capillary origami. First of all, on day one, we learned how to make U gravity negligible, right? And the way you do that is, thank you. You work with small drops, okay? You work with volumes that are much smaller than LC cubed. Then you design the experiment so that the way the regime in which this experiment works is that U capillary is on the same order as U bending. So what's going on is this thing is trying to grab the edges of the film, wet the edges of the film, and it becomes smaller. It's trying to do this. Okay, so the capillary force is what's driving the bending completely. So these two are comparable, and then U stretch is again 0. Okay? Stretching almost doesn't happen. This is the combination of parameters. Maybe a different way of writing this is to say, the system size, I don't know what we've been calling it. I put an L0 over there, so I'll just borrow L0. L0 must be, a few times LBC. I don't know if you remember, we looked at a graph where folding happens successfully if if the size of the thing is 3 times LBC, and it fails if you're at 4 times LBC. It just can't deliver the torque to make this happen. Okay? So that's a different way of saying this same thing, right? That you need to be in that kind of parameter regime. So I'm going to write this actually slightly differently. I'm going to write this as a dimensionless number. So the accompanying dimensionless number is something that for ridiculous historical reasons is epsilon inverse rather than just told epsilon. This is L0 over LBC squared, and that works out to gamma over B over L0 squared. This I've just written the square because it lifts all the square roots. Okay, this is often called the bendability. This number, and actually in this case it's called the capillary bendability. Let's take a quick peek at this. You already have some intuition from this, but this is the scale of the object that's delivering the torque. In this case, it's capillary, so I'm calling it capillary bendability. This is what you need in order to bend the object. It's the torque you need in order to buckle the object, okay? So in this experiment, I would say epsilon inverse is of order 10. Okay. I'm going to now argue that it's actually really, really helpful to change this number a lot. And let's see. Changing this number in the direction of making this object smaller than LBC is useless. It just means nothing's going to bend. Let's think about the opposite direction, okay? And if I were to make a big, big epsilon inverse, what do I have to work with? I have this, but you know, I'm often working with same pool of fluids. And as you saw on the first day, unless you decide to work with, I don't know, mercury or molten rock or something like that, you're stuck with not a big variation here. Here you can go small, but that's not the direction we want to go. You don't want to do these experiments with something the size of a flag. So you don't have much here. What you have is a lot of ability to work with this. You can work with this either by material. Okay, you can change the Young's modulus, or you can change the thickness. Order of, yeah. Surfactant changes by factors of a few. Yeah, you know, I can get from water, I know to get down to from 70 to 10, 15. Okay, I want millions and millions. Okay, and millions are available here because of this ET cubed, which I erased? No, I didn't erase. ET cubed. Okay, so if I change thickness a little bit, so I may make a mess of this. I don't know how well you can see things, but if Iqbal, who owns this camera, can help a little bit, we'll try and look at this. Huh? So, thank you, Iqbal. I could have just shown you a picture, but sometimes it's nice to see somebody mess up in front of you. You know. Okay, so you see a few scraps of things floating around. Thanks, Iqbal. So this fellow up here is a piece of plastic that's the kind of plastic we might have used for capillary origami. Its order of this number is of order 10 if you put in surface tension of water. Okay, and what I'm going to do, if I can, without messing it too much, I'm just going to put on it a teeny drop of water. Okay, I don't know, can you even see that? Can you? Okay, your eyes are better than mine. It's this guy, right? That I've added, okay. Now, there's some other scraps floating around. I don't know if you see these guys. Let me try adding to those, and let's see what the scope of disaster is, as one of my colleagues says. Can you see at all? Can you see what I would like you to see, though? Tough. No, it's the same wetting properties, but it's extraordinarily thin. So what is difficult to see, but maybe just about visible to you. No, it's too noisy, right? Tough to see. Okay, but the thing that looks like a little Okay, is there a place I can stand to make your life better? No. Zooming out is best. Huh? Okay, you're invited to come and check it out afterwards. I've brought more film. You can play with it if you like. If you want to try to float a film and do this experiment later, we can do it together. But I'm not going to be able. Thank you, Iqbal. I'm not going to be able to do it much better at this point. What I wanted to show you is that if you could see it better, I promise you it would look like something like that. Can I stop your screen sharing and do it? It would look something like, like that, okay? You make a huge perturbation, you put a drop and it immediately starts deforming in response. You can see it with your eyes, there's nothing microscopic about it, but it's hard to project. Okay? So what's up with this thing is that it's a much, the only difference between this object, so Shankar asked, is it hydrophobic? No, the big difference is that this is much, thinner. Okay, so all the surface energies are comparable. The bending modulus is comparable. Sorry, the Young's modulus is comparable, but this guy is much thinner. Okay, so we went from thickness of 10 micrometer and a bendability of about 10 to a thickness with these materials. We make them somewhere between 10 and 1,000 nanometers. So, this is the thickness range. You achieve epsilon inverses of 10 to the 6 to 10 to the 8. That's the sort of range you get. And remember this guy, this thing is called the von Karman number. You get von Karman numbers, which is just typical size. Typical size is this. Typical thickness is that. You get von Karman numbers of the order of 10 to the 8 to 10 to the 12. Okay. So we've not done anything really fancy with materials except made the material much thinner. Okay. And I'm going to show you that really gives you access to slightly different behavior. Okay. All right. So what I want to start by saying is that we're going to do capillary origami over again, but with this class of sheets. First thing is I want to say a tiny bit more about why we are so bent on curving sheets into strange shapes. The first thing is, of course, bending is very cheap. Okay, so this kind of bending is super easy. Okay, this kind of bending into a sphere is not so easy. So this thing will not go in both directions for you. And this is theorem. The reason is that if you have curvature in both directions, you must necessarily have some stretching. So this is by theorem, this is from Gauss, this is a result from Gauss. I'll probably get struck by a thunderbolt or something like that, lightning bolt. It's not a result from Gauss. Gauss called it his theorema egregium. This is his distinctive special theorem. And the theorem says that you can't change the Gaussian curvature without stretching. So remember we talked about these curvatures. We talked about one of the curvatures a lot, right? We said that with a material, you can find at any point two principal curvatures. And from them, you can make two invariants. This is the invariant we have used a lot, right? This is the mean curvature. right? Here's the other invariant. So Gauss says, please don't change this. If you want to change this number, you'll have to stretch. So the language is, so this sheet is flat. Obviously has Gaussian curvature of 0 times 0, which is 0. Right? This curvature is 0 in both directions. If I want to curve something in a cylinder, right? This is okay because G is this radius of curvature times 0 in this direction. Okay, so Gaussian curvature is 0 here. And I can very easily do cones as well, right? I'm wrapping for you peanuts in this. That's easy, right? Because again, there's no curvature in this direction. And there is a curvature in this direction. Okay, but no problem because this is some curvature times 0. Okay, so these shapes are very easy to excite without stretching. And this is your intuition. This is why we fold paper into these shapes easily. This shape obviously is not so great because this guy is. These shapes broadly are called developable. You will probably hear chapter and verse in very elegant language from David Mermin later this week on this stuff, okay? But this tells you what we are after with this. Now, I'm going to now show you some capillary origami kind of thing, but with a very thin sheet now. Okay. This is an experiment. I can make it go. Okay. I'm now going to do wrapping, but with a very thin sheet. This sheet is maybe 70 nanometers or so. I'm trying to wrap this big spherical gift. I don't know how much wrapping paper I need, so I will change the size of the present. Okay, we'll reduce that size of that drop till there's enough to wrap, and we'll see how it accomplishes the wrapping. All right. So you got the setting here? Here's a drop of water. This background is oil. We've often thought of air water situations, but nothing different. Here is a sheet that's just floating on the north pole of this, okay? And we're going to withdraw water from here till maybe the sheet's enough to do whatever it wants. Okay, so here's the kind of thing that happens. And I won't talk. Same thing from the top. You're looking at the North Pole now. This thing is just the pipette from underneath that's pulling water. Okay, let me talk through the whole thing again, now that you've seen things. Okay, so here are some things that you saw what you saw, but let me say some things again. As you see this, you almost immediately see that this guy is not a cap of a sphere anymore. It's super thin, but it's not a cap of a sphere. We'll have to ask why not, okay? Even though this thing is so thin. All right, now you start seeing it's flattening, it starts developing some facets here, and then it's very non-spherical, it closes, and then it happily floats off into the horizon. Okay, from above, what you see is already we're at the stage where it's slightly curved. This is smooth over here, but there's a problem already over here. Okay, and it's reconciling that problem by somehow making these little wrinkles. And those wrinkles get a little deeper as you withdraw the water. But now you start seeing this thing is distinctly, some wrinkles are winning and some wrinkles are losing. This becomes, I don't know, 6-pointed, 5-pointed, 4-pointed, and then, it's done. All right. So you get a nicely closed shape. This shape is not at all a sphere. So if our hope was to try and get a spherical package, we got something very different from that. Okay? So we should think a little bit about the sequence of things. This is experiments done by Joey Paulson and Vincent Demery helped understand this. So here's sort of the sequence of pictures. Here's a sheet that's 30 nanometers thick, and you go through this sequence of things. At a very, very early stage, you start seeing that this is not perfectly axially symmetric. You start seeing little bits of wrinkles. We should talk about this. So this is stuff that, please. He's waiting for you with the mic.
Okay. Okay. There is a surface.
Yes.
On top of the surface, there is a liquid droplet. Is that?
In that bottom surface is also a liquid. It's an immiscible liquid.
Okay, right. Okay, and then there is a thin sheet over the sphere or droplet.
Yes.
And
then
you take out the water or the liquid from below, from the droplet. And then you keep looking at what the thin sheet, which was sitting on the top of the droplet, changing its shape and so on.
Exactly.
Okay.
So this is something that you're kind of familiar with. You have a question? Go for it. Go for it, and then you have a question over there.
How did you get such a thin sheet?
These thin sheets are made by a process called spin coating, which is standard first step in photolithography. You'll take the polymer you want, you'll mix it up in some volatile solvent, you put it on a microscope slide or a quartz wafer, you'll spin this thing fast, all the solvent evaporates, you're left with a thin layer of solid. You can control the thickness. You got it? Is that the picture? It's fairly straightforward. You control the thickness of this object by controlling the amount of stuff in solution. The more diluted solution you have, the thinner the object will be for the same conditions of preparation. And the faster you spin, the thinner the object will be. You got the picture? It's drying and spinning and flattening at the same time. Okay, and then you're left with a thin piece of plastic. There was another question.
So I was interested, so when you take the liquid out, so the final shape of the objects which you get, do they peak around the platonic solids, or is there any
We'll talk about the shape. Hold on, Pankaj. We'll talk about the shape. It's an important thing to. Yeah, did you have a question behind? No. So I'll address the shapes in a little bit. Okay. Maybe, yeah. Tell me if you're not satisfied. Yeah.
So my question was, I think that sheet area is too much. If we'll reduce the sheet area and make some cut, it may come into circular shape.
Okay. So the sheet here is not designed in the clever way that the capillary origami sheets were. They aren't cut in designed places. This is a disk. So you start off with a disk on a sphere, and you're saying, you please figure out this problem. You break symmetry as you need to make these shapes.
So isn't it then obvious, because how all the points will come closer, and so we won't get a sphere, right?
Won't get what?
I'm saying if there is a disk, isn't it obvious it won't come in circular form, like a spherical shape?
Right? That's right. So I guess the question is, what shape do you get? What is driving the shapes?
Okay.
Right?
It seems obvious because you see it in commonplace experience.
That's
Okay.
a good.
But
That's a
it
good place to see it. So look, you've seen this problem here, right? In order to make a spherical world fit on a flat map, you need to distort. Pictorially, what's going on is when this thing comes down, if you wanted to fit this, you have to stretch it. Stretching is so expensive now, especially we've made this thing thinner and thinner and thinner relative to bending. So there is too much perimeter here. If this perimeter here and the perimeter here don't match, there's less than 2 pi r here. At the top, maybe you sit flat. As you go further and further, there's bigger and bigger mismatch between your length and 2 pi r. Okay, so you have to do something to get rid of that extra length. The first thing you do is you go in the other dimension and you make these ruffles. Okay, that's the first step of this process. Then you go further and that doesn't do enough for you. And then you go into these shapes that you're talking about. Yeah.
The gear shape that you find,
Huh.
get to this. Only way you can get the edges of this to map line up, hold it to the diameter, and then pinch it on the edges. That's how you make the.
So Shankar is saying how you make gujiyas is how you should get the answer to this. You should line the seal, you should seal the edge up against this. It makes good common sense. It is not something that I know how to prove. I'll show you a construction that shows that that is actually, I'll show you a construction for which that's a good numerical local minimum. You were asking about local minima 2 days ago. The shapes you get, let me talk a little bit about the shapes here, then just remind me, I'll come back to your point. Yes.
So how did you choose the surface area of the sheet compared to the surface area of the screen?
We didn't know how to choose, right? So we chose a big surface area and then we adjusted the volume accordingly, right? I'll give you too big a present. There is nothing you can do to wrap it. So I've slowly reduced the size of the gift for you to wrap, okay?
In the previous video,
Yes,
what do you mean by PS sheets? You have not mentioned. The 79 nanometer
yes.
PS sheet in the previous video. PS means
Oh, sorry, that is the material, polystyrene. Thank you. And just to say, it's a very normal, nothing fancy kind of polymer, okay? We're not relying on clever chemistry. So here's the sequence of shapes you see. Yeah.
As far as I could see, the sheet buckled a little bit on the edge. It's not stretched.
As I'll argue, there is no stretching, as I will argue.
Let me give him answer times 2 pi. The answer, you know raisins. Look at the wrinkles on raisins. That is where the answer.
So you're right, ends up being no stretching. Okay. So, here's a set of shapes and you can ask whether you get gujia at the end or samosa at the end or, okay. And you get a variety of these things. You get a lot of these filled shapes. You get momos somewhere, okay. Here's a clue. When you do this experiment again and again with different thicknesses, this is 8 times as thick as that, which means it's 8 cubed in bending modulus. This is 500 times as unbendable as that, okay? But you get the same sequence of shapes. You get maybe tiny decorations that are different. The patterns here are finer than the patterns that are here, but you get the same sequence of shapes. But this gives you the clue that, maybe all this detailed mechanics is not important. It's okay that we don't understand how to describe every wrinkle in this. So here is sort of how you begin to understand these shapes, at least with a numerical model. So conceptually, the idea is this. Let's say, what have we done here? We've taken this number LBC which compared capillary energy and surface energy and bending energy. And we've made this thing huge. Okay. So the idea is capillary energy beats everything in this problem. So the goal is to say, I'm going to say, I have a piece of wrapping paper and I have this thing that really has to be wrapped. So at any given coverage, what it's going to do is this yellow object is going to wrap as much of the blue object as it can. The goal is to leave as little present unwrapped as possible. Okay. So it's not maybe a minimization problem you've thought of before, but it's statement of the problem is, I give you a volume, please find a fixed area. What's the biggest volume I can wrap in that fixed area? Okay? Like how cheap can you be with wrapping paper is the problem. All right. So this, you can see that to minimize this, there's a free area, and then there's something that tells you the surface energy between these two states. This is pure geometry. There's no material parameter apart from this, and this is just a prefactor. So the solutions for this will depend on nothing. Okay. And energetically thinking about where we've come from, in capillary origami, bending and surface energy were comparable. Here, bending is tiny. So it says, please do whatever you need in terms of bending, free. Surface energy is the dominant thing. Stretching is so expensive that it's a constraint. You say, you don't change the surface area. The rule is you're allowed to bring two pieces of material closer to each other, and material will take care of how it does it. But no two pieces of material can separate. So this is, folding, wrinkling, crumpling, everything's allowed. Okay, and it's allowed for free to first order. Okay, there are solutions for some pieces of this that are clear. The axisymmetric part is, this is not a sphere, right? The top of this is already not a sphere when you start off. This is actually this shape. It's this balloon. And there exist solutions for this from a different Paulson. And of course, Taylor has also put his stamp on this problem. These are the shapes of the object, and the smooth curves are a sphere, and the black dots are the colors are the experiment. The black dots are this axisymmetric solution. But you see, after a while, this thing also doesn't look axisymmetric, right? It doesn't look an axially symmetric object. It looks weird. So you have to go beyond this. This is the Taylor solution. Taylor thought of this problem because during World War II, he was asked to work on parachute shapes. So this exact Paulson shape is in Taylor's study, constructed with the silk parachutes. So there's a good solution for that. You can constructively make other solutions by doing something like capillary origami. You can say, okay, I can divide my disk up into little pieces. This is the spirit of stuff that Shankar was asking. And maybe you can make these things coincide. You can wrap up this piece, you can fold this piece away, and then you get one flank of this. So you can make 3-petaled objects, 4-petaled objects, 5-petaled objects, things like that, okay? And you can do a pretty good job. With simulation, you can actually just try a straight minimization of this object. And our colleagues did a pretty good job in describing the overall shapes. Excuse me. We don't know, you were asking about exactly what shapes. These are not platonic solids. These are all typically inflated shapes. They come from taking polygons and blowing air into them till they stop stretching. Many of these shapes, for example, the 2-fold and 3-fold, they are really very comparable in energy. And I don't know of a good proof that the 2-fold is the best fold. Okay. We know it's better than other folds that the simulation has found. So this does something actually for you that's remarkably different from capillary origami. And this is what you get out of going to much different length scales. Okay, So by taking this number of 10 and saying now, please work at a million and above, where bending is for free, pure bending allows you to get many, many, many unusual shapes that you couldn't have imagined that you could get just by bending something. Okay. There's a whole world of things that now people are discovering you can do by cutting with origami. I just want to make the point that bending also gives you access to an extraordinary range of shapes. Yeah.
Does these things show up?
This is millimeters. This is millimeters.
Yeah, but I'm thinking about,
Meters?
no, yeah, a couple of centimeters maybe. Shapes of pumpkin surface or papaya surface.
Not sure. Yeah, I think those are not inflation problems. Yeah, I think those are growth. I think those are growth problems where the shape is dictated by how quickly you grow as a function of time. It's typically, you can get very complicated flower shapes this way. I don't know about closed shapes, but flowers, cabbage, these kinds of things come from, they come as growth. So we have a quick way to do this also. Instead of that slow painstaking experiment, you come with a drop of water, you punch through the sheet, okay? And in a small amount of time, you have, through this is a very, very violent process. But again, there was a question here about how quickly can you do all of this? How quickly do you care? Elasticity works very quickly, okay? So this shape is pretty nice. And in spite of its violent birth, it actually has a perfect seam. Okay. This is perfectly sealed object. And now you can start playing games. You can start doing it with, instead of discs, you can start doing it with other weird shapes. This is a net that will fold up into a tetrahedron, net that will fold up into tetrahedron. Again, you manage this very good seam. So this is another sign that the capillary energies are so large. This guy will not keep the curtain open at all, right? You will shut the curtain as best as you can, all right? And once you shut the curtain, there's no reason to go further, which makes this thing reversible. It won't go like this and stick to itself, okay? So you can open this package quite easily as well. Okay. So you have probably seen these things like in cushions, you'll get straight, you'll get shapes that are curved in overly stuffed furniture and cushions and things like that. I always thought that those are because of stretching. That's not true, okay? Having a concavity in the cushion actually produces more volume somehow. It's without stretching. You're managing to pack in more volume because you make the corners longer and you make the side fat. There's a trade-off there. You feel like you're wasting space because you'll see wrinkles in your cushions when you have them stuffed. You're not. Those wrinkles are doing something. They're taking away extra material somewhere so that you have the freedom to bend in some other direction. So those are not overstuffed things at all. Okay. So maybe this is, I'm going to move away from this problem a little bit, and I want to walk towards another problem. Maybe I'll show you a harder version of this, again from the ESPCI group, and this maybe I can do without this. I'll just try to make a mess straight on the table. And instead of wrapping an object around a fluid, I'm going to wrap it now around a solid ball, and let's see what it does. Okay. If there are disasters, Mahesh, I'll count on you to pick me up off the floor, but otherwise I'm fine. Thank you. So here's the goal. So downstairs lab has a little surface lying around like this. Okay, this is sort of hemispherical, it's a spherical cap at least. And what we're going to try doing is wrapping this. So you know that just brute force wrapping is pointless. Well, we can do it, right? You end up with a whole bunch of defects. You can end up with, right? This is the kind of thing you'll end up with. So let's try and see if we can do it more gently. And let's see if capillary is helpful. Okay. So for that, I'm going to first wet this object. I'm just going to wet this. You can do this yourself, but don't use something that's not wetting. Don't use plasticky things where the water runs off. Use wettable surfaces, use glass or something. Again, try to use something that wets over here as well. Try and use a sheet that wets a little bit. Is it possible to get at this from above a little bit? Okay, maybe. Can I point and will you see better if I do this? Okay. You see this blobby object? Okay. I can do my best. I can't get coverage. Okay, but I get these weird animals over here. And I don't know if you see this, the animals change in shape depending on what I do, but the scale of their limbs doesn't change too much. Okay, there's a characteristic scale I get over this with this. Okay, thank you. Let's think about this one. All right. So obviously, if I had this and I took a thin strip and I did this, no problem, right? I can get the whole strip to lie on this. It's just when I wanted to bend this way and that way, that I start running into trouble. Damn it. Okay, so let's think about this one a tiny bit and see what we get out of it. And I will only spend a tiny bit of time on it. So the minute you have this wet sphere, here's the sphere and it's wet, it's blue, so it's wet. Okay, and here's the solid. Okay. This time now this is rigid, right? It's not like the thing that I was showing you earlier. So the question is, so here is, sorry, this is not meant to be the whole sheet. This is meant to be one of those little pieces that manage to stick on. Okay, and I'm trying to ask, what is the size of the sheet that can stick on? Okay. So here is finally a place that we can see the effects of stretching. If you get some sort of smoothly curved piece that is adhering, that means it's stretching. How could it otherwise, right? So let's see what the scale is like. So the first thing is, we talked about, there's some excess length associated with this object. This thing around here has too much length to deal with. Okay, so there has to be some strain. So the strain is on the order of some excess length divided by the characteristic length of the object. And I'll put this in the notes in some detail, but this is on the order of, this is the radius of curvature of the object. This is the L that we're trying to think about. Okay, I won't work through the geometry right now, but I'll put it in the document that I have. Now, there's actually some strain energy now. So the strain energy is, at least the strain energy, the strain energy density is this times strain squared. Okay, times the size of the object that's getting covered. Sorry, by L squared. This is the strain energy density. This is the per area thing that we wrote far end of the board. Yeah. Y times strain squared times area now. And the U for capillary is, you manage to cover pi L squared area And everywhere you did that, you saved some water from seeing the air. Okay. This is driving the process. This is hurting the process. If you balance these, you get a scale that looks like size of the blob is something like gamma to the 4 divided by y. As I write this, I have the panicky feeling that I've got some dimensions wrong. Okay. But here finally is an example of Gaussian curvature. I should have actually shown, sorry, I should have shown you these guys, they make experiments look so nice. This is again the ESPCI group.
Is it possible positively curved surface or even saddle will show you this?
Saddle will show you blobs. Very good question. I'm not showing you more of these. Okay. I'll show you their pictures, which look much prettier than I have done justice to. You get, if you do a better job than I just did, you start seeing these patterns proliferating. And you can play a little bit with the geometry to see, well, if you do a thin band, if you do a point source, if you try to bend it in an annulus, you get the same scale. There's no escaping. Okay. Okay. So this is what we said we'd start off with. We'd start off with trying to excite stretching modes by trying to make things curve in 2 directions. We saw that if you go to highly bendable sheets, there's an escape clause. It'll somehow find a bending mode. When we put a more rigid constraint on it, you start first seeing stretching creep in. I want to follow this path now in a different direction, which builds on our old stuff. Okay, remember the path of this guy had 2 cousins, right? 2 parents or whatever. Yeah, those are the young Laplace-Dupre 3-phase contact and the Neumann 3-phase contact. Okay, and now that we've started talking about thin things, I want to show you the other member of the family. This is here. Young Laplace is, of course, shouldn't do it this high, right? Here's young Laplace. Here is, here's Neumann. Here's this. One other member in this family now you can think of, interpolating between a rigid and a liquid substrate, is this guy. Is now a deformable sheet, kind of what we tried to do and you couldn't see very well on a drop on that. Sorry, that's a horrible drop. Yeah. Now, this thing, obviously, you've got to hold this guy up. It's not going to stand in midair. There's 2 ways you can do this. You can either clamp it on the sides. Okay. You can build a clamp like that. Like a drum head. Okay. So this thing is sitting, held by the clamp under tension from everywhere. Okay. There's tension pulling it here. A simpler way of doing it, and a more controlled way of doing it, is very hard to clamp one of these objects perfectly, right? You can imagine trying to take something as flimsy as the stuff we saw and trying to trap it in an annulus like this, is take this object and just float it on a fluid. Okay. Like we did over here. Okay. So the question is, for this object, first I need to tell you what's the tension in this object. Just here, it's straightforward. It's what I do with it. It's how I clamp it. So let me try to tell you an experiment that's more or less designed to measure that tension. And I think it has in it a nice sort of little elastocapillary lesson as well. And I want to walk through that a little bit for the last half hour we have together here. Well, that sounded very fine. Okay. So let's start off a little bit earlier. Let's start off by thinking about sorry, I've lost my cursor. And then smash the invaluable Hagomore. Really sorry. I am sorry about this. This is a place where I need. Okay, I'm going to try, huh? For some reason I've lost my cursor. Not a nice time for me to lose my cursor. Okay. Sorry, I'm struggling to go into slideshow is what's happening. You're watching, huh? Am I okay? Okay, so the first thing is, we should have probably talked about this a little while ago, but why does the sheet want to go to the interface at all? And that's the kind of reasoning that you're actually pretty well equipped to handle now. If you release this object somewhere inside the fluid, and now say, well, would you prefer to live in the bulk of the fluid, or would you prefer to live at the interface? Then you determine the following. You say, okay, inside here, I have 2 gamma solid liquid and an exposed piece of surface. In the end state, if it's on the surface, I cover that piece of surface. I still have 1 gamma solid liquid and I have 1 gamma solid vapor. Okay? So if this is better than that, it's going to go to the surface. All right, so this is, you will not be surprised to see this is just like a wetting problem. This is our old friend delta gamma. Okay? And this is gamma LV, which is the thing that, so this divided by this is the cos theta we used to write. Okay? Good. So it goes to the surface if it's there. I won't show a movie of how it's going to get to the surface. You can ask me later. It's on the surface, and once it's on the surface, it wants to lie flat. Why? Because that's the reason it went to the surface, to cover as much of the surface as possible. So this thing must be under some stress if it's being pulled taut, right? So what is that stress is the question. Yes? Yes. Oh, very good. That's a step. So the question is, okay, you've compared the surface energies in this situation and the surface energies in this situation. How did it know that this other state existed when it was swimming inside the liquid, right? That's a perfectly legitimate question to ask. You have to do something else to introduce it to that surface. Either this has to diffuse to the surface, or gravity has to get it to the top. One of those things has to happen. No, that's not that's a separate question. The dynamics of how it gets to the surface. Okay, so now the question is, what is the surface? What's the stress over here? Okay, so 2 possibilities. We use all our familiar characters, and you could say, hey, there's gamma LV here, there's gamma SV here, gamma SL there, and the same thing on the other side. Okay, maybe these are the characters. Or I don't know, maybe it's just the stuff that's acting on the edges. So I should tell you that if you look at the literature, these are represented in almost equal numbers. And only one can be right? It's a stress. There must be some value of stress in there, and it can't be gamma LV minus gamma SV plus gamma SL and gamma LV. So you're invited to please at least mentally vote. Okay. Everyone's mentally voted? A or B? Okay, so now we'll go on and discuss an experiment that tries to probe this, okay? And the experiment is quite straightforward. You take something like a clothes hanger. So this is a little carbon fiber, and you pick up this liquid, you pick up the sheet off the surface of the liquid, okay? And this is an experiment from Deepak Kumar. Let me try to tell you why this is a useful way to think of things. Yeah. So here's a solid, and here's the water interface on one side. All right. How do you think about the solid? Well, you think about the solid using all the stuff we did yesterday, which is, you say this guy is, it's got some bending and it's got some stress on it, which couples to the curvature. It keeps the length constant. And then, there's rho GH because this thing is a meniscus, right? And on this side, it's what we did the very first day, the calculation of rising up against a wall, right? So it's gamma LV times curvature plus rho GH. So this is H liquid of X. This is H solid of X. And kappa is just the usual thing. You can put in all the things that we did the other day, right? Is this guy. All right. So one thing we said is we're going to deal with very thin sheets. Bending is almost free. Even those fine kink bends were for free. Well, then I'll prove it to you further, but let's say we take this out of the problem. All right. As soon as you do that, you realize these are the same equation. One has gamma LV in it. One has the unknown sigma that we're asking questions about in it. So we'll find out what this shape is. We'll find out what that shape is, and we'll compare. Okay, that's the game plan. Okay, so when we do that, or when Deepak does that, he sees, so the experiment is set up like so. There's this thin polymer film. From a distance, it looks almost like a right angle bend. So you laser slice through this surface. There's a little bit of dye in the water. And that corner looks a little bit like the meniscus I drew. Well, I'll just show it to you now. Okay, so here's what it looks like. And at this point, I would like a question. Okay, I'll tell an answer then. The question is, where's the sheet? And the answer is, the sheet's on the left, the liquid's on the right. Okay? And the reason you have to ask this question is because there's nothing distinguishing it. They look the same. And in fact, they more than just look the same. They really, really are the same. So here is a digitized version of that image. Here is the profile. That's the surface of the water, the blue dots. That's the surface of the sheet, the red dots. That's the nonlinear Young-Laplace equation. It's that thing with all nonlinear stuff in it. And they sit exactly on top of each other. Okay. So the conclusion is, okay, the conclusion is yes. So that if these shapes are exactly the same, these two numbers be exactly the same. Yeah. Okay. Here's just more data in support of this. here is a few these curves are just shifted for, and it's now log linear. They're just shifted for clarity. These are a whole bunch of polystyrene films of increasing order of thickness. This is meant to show you that the thickness didn't make a difference. Okay, the bending is that I was valid in neglecting the bending. Okay, so the fluid and the solid sit exactly on top of each other. You change the solid, nothing changes. This is PMMA, different polymer with a completely different wetting angle. With a completely different wetting angle, but you get exactly the same slope of that curve. The minute you change the fluid, things change. Okay? So the stresses in the sheet are purely determined by the liquid vapor surface energy. The solid surface energies are irrelevant. Here's a way to think about it, or at least a way we thought about it. So imagine you take this object, which is at some happy length inside this liquid, now bulk, just to make things simpler, not at a surface. Now you put it in another liquid, and let's say it's happier in that liquid. There's lower gamma solid liquid in here. It might expand modestly. Okay? It might get slightly bigger. You can also leave it in the same liquid, achieve that same extension just by pulling it. Okay? These two cases aren't the same thing. And a simple qualitative way to say it is, push it with your finger or cut it with scissors. This guy will fly apart. Okay? This guy will fly apart. This guy is perfectly happy sitting there. Okay? So what I'm trying to get at over here is the following. Change in dimensions can happen. For those things, the solid vapor, solid liquid energies are important, but they don't amount to stress. They amount to sort of a change in ambient conditions at some level. Okay? It's as if you've changed the temperature here, the solid surface is readjusted, and it's come to some new reference state in which it's perfectly happy and relaxed. Okay? So the solid vapor minus the solid liquid is extremely important in telling whether this thing will go to the surface. It may have some subtle influence in telling what the equilibrium state looks like, but it doesn't make a stress. So let me skip this. Somebody asked earlier whether this is the real contact angle or not. But let me go back here first. Yeah, just to be sure we're all on the same page, because this is the page I want you to be on. The correct answer is B. Okay, and please let's not write papers that say the correct answer is A. If we can agree on that, we'll be friends. Yes.
So in first picture also, if you are doing mass balance overall, those internal will not come. So I think first one is also correct in one way.
This one and this one cannot both simultaneously be correct. Right? A stress is a stress. It's a measurable object.
So if you are doing force balance only at a left side or right side?
You can ask what the stress in a material is, right? You draw a line through the material and you say, the left side of the material is either pushing or pulling the right side of the material with some force. That's the stress, no? There is no way to argue your way out of saying there's two possible answers here.
So, okay, I was saying if I do overall force balance, those will come like a kind of internal forces, those won't come, then gamma liquid vapor only will be cancelling other gamma liquid vapor.
Stress is an internal force as well. Okay?
Yeah.
But what I'm trying to insist to you is, even internally, this thing doesn't have integrated over its height a new stress in it. Maybe I should show this thing that I showed over here. So imagine now cutting a chunk of imagine cutting a chunk of material out of bulk. And now I bring it out into the air, naked to the world, and now it has to deal with the fact that it's got no neighbors near its surface. Okay? This guy is something is going to change about it because its surface conditions haven't changed. Okay? For example, there may be, this may contract. What I'm insisting on, what the previous experiment showed, I think unambiguously, is that the integrated thing over here, which is the thing that we've been focusing on, right? The height integrated is 0. This guy may have to do something complicated interior, but integrated over height, it's 0. Yeah.
Yeah, I got confused because I thought after cutting, we are again generating 2 different corners.
Once I cut like this.
Yeah, next picture, yes, and same thing.
Here,
So now again, force will be acting.
no, there's no force here. This thing
Yeah,
will be
inside,
unbalanced.
but
This will
at the
slowly
surface.
push off there, is the idea. The only thing that will be acting here is gamma LV.
Yes. But at surface will be different, right?
This surface and this surface.
No, at the surface of the liquid, if that sheet is floating and we are cutting.
No, importantly not also.
Okay.
There will just be in the case where there's gamma LV, each piece that you generate will also be under tension.
Yes.
Okay.
Yeah.
But if I cut this, if I hold this in a clamp and cut it, it will
yes.
do the same thing. Okay. I think I was going to tell you some things about what goes on at a smaller scale. I'll say this very quickly because somebody asked earlier, if you zoom in, what does the contact angle look like when I was talking about the wetting ridge? Is the contact angle really the same? And I wanted to say, the picture we've been looking at is not the contact angle at all. Okay, I showed you a nice symmetric picture. This is the scale of L capillary. We're zooming into millimeters. If we zoom in even further, then you'll see the fact that this thing doesn't look symmetric. Okay, so here's the kind of picture we've been looking at. Now, if I really zoom in here and look at the Bandyopadhyay scale, now you don't need to ask me which side is the sheet and which side is the liquid. Yeah, you don't need to ask me, right? This side is the sheet. This is an elastica over here. And here is the true contact angle. Okay. And all these things are connected in some way. The force that you need to hold this up at a macroscopic scale, this cuspy thing that you see, this local contact angles are really all the same thing. Okay, I have maybe not time to actually finish that, but I wanted to say a few words about that last 3-phase contact angle. Yeah. In this case, it's liquid vapor. So the question is in the one with the blob, the wrapping a solid sphere, rigid sphere, what is the gamma? There, the gamma is liquid vapor. Actually, I used alcohol over here.
Yeah, so the gamma for the sheet doesn't appear.
Gamma
Is
for the
that the
sheet
same
appears in a
reason why-
subtle way. Gamma for the sheet appears in that it should wet it. If I pick a sheet that doesn't get wet by water, so it appears the same way as it appears in this problem. I wouldn't even get a sheet at the interface if that delta gamma wasn't a positive value. Thank you. Okay, maybe I'm going to end with the last comment on this object. So, what I wanted to say is, when I look at a problem like this, okay, now when I put a drop on this, when I start off with the sheet, what I've tried to argue is that internally, the stresses are just gamma LV. Okay. Option B. If you voted option A, don't feel bad. Many people have voted with you. If you abstained, I have nothing to say to you. But here you put a drop. Now, things can change, right? First thing that's going to change is this guy may deform. It's feeling Laplace pressure, right? This looks very, very suspiciously like the Neumann problem. But it isn't. That's the one important thing I wanted to leave with you. When I look at this curve, this object, bigger, I originally started off with stress equal to gamma LV. I'm winding up in a second. Okay. But now, as soon as I put the drop, these stresses will change. Okay. Unlike the Neumann problem, where if I put a drop on an interface, I get the gamma liquid 1, liquid 2 interfacial energy. There's nothing I can do about that. Here I have, here I have a sigma in the dry portion. I have a sigma in the wet portion. And I have old friend gamma LV up here. Okay. And I need to figure these out ab initio. It very much matters whether the perturbation is big compared to the original tension or not. There is no real convenient way of backing out things. In fact, in this high bendability version that I've been telling you about, this thing has very non-trivial scaling. It has a very non-trivial scaling with what with the parameters of this thing. Did I write it down for you? I think I wrote the whole thing down for you, but yeah. In fact, here, sigma wet is sigma original is not a good starting point often. You can make a huge change to this problem just by putting that drop on. Okay, and for the high epsilon inverse version of the problem, sorry, we didn't get to see you. We spent a lot of time looking at what the base state was. As you can see, the base state itself is confusing, but once you understand the base state, to put the drop on and try and figure out what the stresses are is yet another problem. It's really, really not. You remember we did with this fellow, we did 3 happy force balances with forces we knew. We had 2 unknown angles. Remember, we had an angle above the horizon, an angle below the horizon, and we had 2 force balances, vertical and horizontal. Again, there's lots of stuff which uses exactly the same equations for this. Not true. Okay. This is, you have to solve the full elasticity problem again. You can see this thing form. You know now that if this thing forms a spherical cup, it's got to have stretching in there. Something new must be in the problem. Okay, and those things won't come as perturbations. They won't come as original stress plus small corrections. They'll change the whole game. Okay. I had hoped that I could finish that full family for you, but I haven't been successful in doing so. I just wanted to go back to the very beginning. I just wanted to remind you we did very few things. We left out almost everything that was inconvenient in life here. We did simple elastic solids, no non-linearities, no plasticity, no changes, no microstructure, no kinks, no folds, many things you can add is what I'm saying. Same thing with the simple liquids. There's a lot that you can add to play with. The good news is if you're trying to solve an applied problem, there are many, many, many knobs here to tune. If you're trying to understand something, my strong encouragement to you is pick one thing to play with. This is not difficult to find something new by using lots of ingredients. Pick one thing, and I would strongly, strongly encourage also try to set up an experimental setup in which you're in some asymptotic regime. Don't be in a state where everything is comparable to everything. You don't know who the criminals are here, and everyone has some share in the final shape. We won a lot by going to extremely thin films. in these situations, when you're in conflict with theory, conflict is large. You know, there's a big difference if you don't get it right. So I would, again, push you, if you were to work in these things, to try and find some corner where you can, you know, find an extreme. I'm going to stop by thanking a bunch of people. This is about, we've been working on this for, 10, 12 years. So that is sort of 3 PhD lifetimes. So I've learned a bunch from different people. So thanks, Mahesh, Ranjini, and all of you for making it through 3 days. But here are a few of the folks who have been working on, at least the stuff I showed today comes mainly from these folks, but I learned things a lot from students who worked on these earlier. I also want to say that this is kind of a generous field. People have been very helpful in helping me learn things. And I've worked a lot with my theory colleague, Benny Davidovich. Okay, folks, thanks. So please say questions, answers, comments, jokes. Yeah. He's telling you to wait.
Go back to this question of a saddle, because in a positive Gaussian curvature, you can do away with stretching. But if you have a negative curvature, you have to contract, compress it. Now, is it that compression and stretching similar or different in this problem?
Okay. Compression is generally easier to take care of in a thin object because you can easily absorb extra length in folds, right? I think the trick with, I would say a tricky thing about doing one of those experiments on big scale is, to start seeing. Let me think about this a little bit more. My feeling is just in terms of the elasticity, there's no difference, right? That stretching modulus is for compression or for stretching. That's just linear elasticity. I'm trying to think of a clean geometry in which to do this. But my first response is it's probably no more difficult to do it in a saddle.
Yeah. What Young's modulus is for whom?
This Y is not Young's modulus, it's that stretching modulus.
Stretching for which material?
It's for that thin sheet that I'm trying, it's for my wrapping paper.
Right. Okay.
It's the Y of the wrapping paper. There, the blue thing, sorry, it's for the first time in 3 days, that blue thing isn't a liquid. That thing is a rigid solid. That blue thing is this guy. And so elastic modulus of that guy is not in the problem. It's so rigid that nothing's going to happen.
That expression, I was thinking, it's a small, nice experiment can be made for UG students.
I made a small, nice experiment for
I
PG
mean,
students.
no. What I'm saying is, we can give them, just like you did the experiment, you
Sure.
can ask them to take the picture and then map it to a circle, calculate the L, and then finding out gamma or
Please.
Y.
Do that, send me a postcard. I think absolutely doable. Many of these things are actually quite doable. They're a little bit sophisticated to think about, but I think they are very common experience. So at least you can start thinking about them empirically. Once you start thinking about them, there are sometimes little traps.
I have a question about the thought experiment. So I'm wondering if we put a thin sheet on liquid, does that, I don't really know what this question is, but does that diminish the ability for this solid or thin sheet to sustain stress? So, okay, I have to explain this a little bit. So if we think about just like a one chain of balls connected by springs. And if I try to apply force from one side, then I know that the spring here would definitely exert more forces, like it's cumulative, right? This part will be
Oh, no,
less
right?
force. Right. But I mean, if it's a thin sheet, it's dry, it's just in the air, then I would expect it to act like that. But according to the thought experiment, you can, you get nothing by creating them, making small pieces of them, right?
But this is true, right? If I have a thin sheet just sitting on the surface, at least if nothing is flowing, then that stress is actually just continuous right through, like your chain. It's one single value of stress on the whole thing. The minute I start putting, and in 1D, it's even stronger constraint, right? I can start poking here, and at least in pieces, it's continuous. In 2D, suddenly the picture changes, right? In a situation like this, even here, forget all the subtleties here. The stress outside is no longer uniform, and it's no longer isotropic. So 2D suddenly changes the game a little bit, which is why I slowly backed into it. Am I making sense? So you say you have an object under tension, uniform tension from the edges. It's isotropic, it's uniform, just from stress balance. Now I start poking it in the middle. Immediately the stresses everywhere will be anisotropic and position dependent. But until that point, I think your chain is perfectly okay to think about. So I think just with a simple geometry like this, and it's just floating static, the stress inside's got to be uniform, right? Just for stress balance. I think somebody else was, maybe you were saying, how do you get force balance inside this, right? For that, I think we just have to have stress being uniform. But the minute I put a perturbation here, and actually I'm arguing that this is not a perturbation, this is a huge change, then stresses are no longer spatially uniform. And as Mahesh was saying, this direction and this direction are different. They become anisotropic. Hence that picture we saw with the weird wrinkles. That's being pulled along the radius, but it's like a skirt. It's being tightened in this way. Any other?
So I was just wondering, in that case, we had one single sheet, right? So instead of that, if we have some smaller sheets all over the bubbles,
Yes.
so that time we may get.
That's a nice
this
question. So the question is, can I get good coverage by slicing this up into little bits?
Yes.
And can I cover the whole thing? I certainly can cover the whole thing. Yeah, that's absolutely right. That will give me better volume coverage then. I don't know the answer. We haven't explored the answer to this question, but certainly the direction you're going in is right. There is mathematical literature about this. These wrapped chocolates, these round chocolates. There's some mathematician who spent a year trying to wrap chocolates with 1 piece, 2 piece, 3 pieces, which is a nice way to spend the time. But I don't know the answer for this problem. Clearly, your intuition is right. The more pieces, the better coverage. But are you talking about this? Sorry, are you folks talking about this problem or the problem you saw on the screen with the big drop?
That only. This also both have the same physics behind it, right?
In some ways, no. This is the physics of stretching. That is only the physics of bending. But you could ask the same thing, you know, if you had many pieces in which you have many LBC but not a single piece, do you gain more? And you know, how can you gain less? Right? You're going to gain.
Yes, like,
Hmm?
because yeah, thing, you know how to, you need how to steam it up.
Yeah.
But if you do it like random particles, you don't know how to.
Oh,
steam it up.
random particles, I don't know. But
So it
you
has
know,
to come from
if
different
you're,
places,
if
not fully cut out particles, because otherwise it's not.
random particles, I don't know the answer to. You can certainly frustrate this. You can certainly frustrate this by some particle shapes.
Steaming, that steam that you get either the end.
So let's do a trivial example, the early stage of this, right? Where it's the Taylor solution or the Paulson solution, two things sewn together. If you try to do the two things sewn together by one sheet, you will lose a lot. There'll be a lot more wasted material. This is much easier. Yeah, 2 halves is easier. I'm sure there are pathological cases.
So for like,
You're probably right. There's cases where it's not going to help you. But by and large, I think more pieces would be good.
using like pentagons and hexagons, we are able to cover a football. Like with seams.
Yes,
That is like what.
you could do that. That's I don't know how. That's right. Hmm? That's unfrustrated, yeah. That's right.
More questions?
So you didn't really explain the shapes at the end.
I didn't explain the shapes because I understand them. I understand that the shapes come from the simplest equation I could show you, which was this. Okay. I can explain the shapes in the axisymmetric shapes in detail from this. The other shapes, I just know that they're local minima of this object. I don't know that for example, an important question we don't know the answer to is the transition to polygonal shapes sharp? No idea.
So I couldn't solve it in my head, but it wandered.
Thank
into-
heaven, Mahesh.
Wandered in 2 orthogonal directions.
What's that?
I couldn't solve it in my head myself, but my mind wandered in 2 orthogonal directions. One is puckering of a tennis ball. When I try to pucker it, I get a 3-point, basically 3 dimples, a dimple with a triangular dimple. And I tried to work out if this is the reverse of that, but that went nowhere.
Look,
This-
it's a little bit in the same spirit. At least the constructive solutions I showed you, it's a little bit in the same spirit. I know you have a second thought coming. Let me address your first thought first. The constructive solution I showed you is made by taking many pieces, and like your polygonalization of the tennis ball or the TT ball. You say I'm going to somehow in there actually you pay a lot for those corners. Here you don't, it's for free, but it's the same idea. You take pieces and you fit together something that has, n-gon symmetry.
Second was, let me draw it because
Please draw
it's
it.
easier.
Please
to
draw it,
visualize.
dance it.
When we think of raisins, take a dry raisin and throw it in water and then pull it out and let it dry. And this is the swollen raisin, and as it dries out, the wrinkles form a lot, sort of like this.
I should stop sharing so that people can see you.
This region has higher radius of curvature, whereas this one is less than this one. So the wrinkles start forming along the longitudes, right? So something along the same lines was happening on for the sheet that was wrinkling, but there are fluctuations that amplify in the end to give you the triangular, the
Okay.
3-point shape.
Okay.
And the point where I got stuck was, is it due to the length scale that emerges due to the competition between bending and stretching, which is the square root of radius times the thickness? Square root of
So the scale in that problem is in the resin problem is something to do with skin thickness divided by something to do with the substrate, the elasticity of the substrate, square root. Problem statement here was tiny bit different.
Yes.
It's not, I'm giving you a fixed amount of area and you're perfectly packed in the beginning and I'm extracting area away. Problem statement here is, I'm giving you a fixed area. Please wrap as much as you can in with this. But I think the architectural piece here is similar to the argument. The
Yes.
cost of this is there, but
But this comes out dead in water,
as
whereas that doesn't.
as I've tried to say there, those architectural pieces I just forgot about. I said they're almost free, and I haven't thought about exactly where they.
One final question.
Please,
Where you
but they can have final questions. as
They're
well.
not asking.
Okay,
I have even tried to intimidate them by standing obnoxiously in front of them.
okay, don't do that.
So
Don't do that, please.
imagine the situation where you showed the thin film being pulled up and you asked which side is the solid and which side is the liquid. And you were very careful to point out this is when there is no flow.
When there's no flow, yes.
Have you studied the situation where there is flow?
Okay, we've done of a certain kind. I think I skated past that. The problem that we cared about to start all this stuff up with was this guy, Mahesh. I don't know if that's what you mean by flow. We were interested in how this guy gets to the top. We said that this was the before and after, and people very correctly said, well, how did it even get there? You did, no? So here, this is driven by gravity in this particular example. Here's a sheet sitting over there. It's rising under gravity. Okay, it's buoyant. And this guy does what it does for a long time. It's near the surface and it doesn't quite know, I need to get onto the surface to get advantage of that huge surface energy. So it's sort of hanging around there for a while. By the way, it moves much faster through the fluid. And then it turns the corner. And now it decides, I can go. So this is the kind of, is this what you meant, Mahesh? Or did you mean, I hold it statically and have a flow go by? Not really. I mean, there's a whole range of people who have worked on these flag fluttering problems.
It's actually related.
Is that what you're thinking of?
Tears up in two orthogonal directions. One is the famous Landau-Levitch problem.
Okay.
Right? You're pulling a sheet out of fluid and you're watching it drip. The second is what is known as the McCutcheon D line or the Thoreau-Reynolds ridge. Thoreau being Henry David Thoreau.
Okay.
He shows up in science too.
I'll have to learn that second thing from you. We've done some version of Landau-Levitch, which is just tugging this thing out. Even without the fluid, by the way, this is a great way of measuring. I'd like to advertise this as a good way of measuring contact angle dynamics in general, hysteresis in general. I'll have to tell you more about that separately. So that kind of slow, quasi-static creeping up and down we've done. But I think you have something else in mind with Thoreau and.
This is not very different from film of surfactant with flow of fluid below. And at the point where the surfactant and the underlying fluid meet, there is a discontinuous line. And it gives rise to a ridge, very similar to this.
Okay.
So both problems have an elasticity involved. Surfactant also has an elasticity involved in the surface tension.
Okay.
So I'm trying to see if you studied that case, so holding this static and flowing the water, because that would map to the
haven't done that at all. All we've done is small, slow movements in and out of this thing as a way of studying contact angle kinematics along that line. But no, I'd be curious to know. No, he's talking about he shifted to another one.
There are two ways to study. Both are unrelated. But the setup is
I'll have to ask you about this. There's nice advantages compared to a sessile drop. There's a large pool here, so evaporation can be taken care of very nicely. The contact angle is a long line here. Measuring is very high precision, and I don't know, we looked at this a little bit, maybe it stepped up. So you can measure out at this scale, you can measure the force, and you can infer what's happening at a much smaller scale. This is a little bit like Wilhelmy plate measurements in spirit. There is, you can't get anywhere, you can get much higher precision with this because the Wilhelmy plate actually has a big buoyancy correction. This thing weighs nothing.
Yep, I'm sorry, I have to stop the question session. And let's thank Menon again. And if you have more questions, yeah. please come back.
Yeah. Thanks a lot, folks.